Here are two brainwaves. One looks ugly, irregular, looks very arrhythmic. Here's another one that looks extremely regular. Nice round wave followed by a sharp wave. Round wave followed by a sharp wave. Which one would you rather have? And the answer is that the upper one, the ugly, irregular one, is a normal adult EEG. The bottom one is a spike wave complex of an epileptic seizure, which is a very dangerous and very pathological condition. And the moral of the story there is, I think that order is not always good. In brainwaves, at least, this kind of order is pathological, and a chaotic-looking EEG is a healthy one.
This experimental data looks quite normal. An irregular, healthy EEG at the top, a regular heartbeat, and a smooth respiratory cycle. Two of Garfinkel's colleagues have studied the effect of one drug, cocaine, on these rhythms. In goes the cocaine. Now the EEG resembles an epileptic fit. The heart is fibrillating, and the breathing cycle is irregular. One drug has caused pathological order in the brain and pathological chaos in the heart and lungs. In a laboratory in Philadelphia, a subject rests quietly while his brainwaves are being recorded. It's called an electroencephalogram, EEG. If a healthy brain is chaotic, it should be possible to find a strange attractor for mental processes. Though a skeptic might wonder what such a dynamical analysis could usefully tell you about the endless chatter between billions of nerve cells that occurs when a human being is thinking.
One might consider it's analogous to hanging a single audio microphone over Beijing. One could not possibly begin to understand conversations. But in fact, there is some information to be learned. If you were to record for a sufficiently long period of time, you would first of all discover that there's about a 24-hour cycle to the sound that you're picking up. And if you continue to record for even longer periods of time, there is a certain seasonal variation. People are out in the evenings longer in the summer months. And in fact, on a few very special occasions, such as a New Year's celebration, there will be annually a very abrupt transition of behavior, which nonetheless reproduces itself. So by hanging a microphone over Beijing, you are not going to learn Chinese, but you could in fact learn something about the collective behavior of Chinese urban populations. And this is exactly what one is doing electroencephalographically. If you take an electrical signal recorded from a subject at rest and perform the kinds of mathematical analysis that one does for signals from fluid experiments or electronic circuit experiments, in fact, instead of getting a very complex, random kind of pattern of behavior, you get a very simple and visually very beautiful kind of a pattern which corresponds to a very low-dimensional attractor.
In order to find out what happens when the subject is mentally more active, they get him to count backwards to himself in sevens. A not-so-easy mathematical task. They do a new dynamical analysis, and the attractor changes. It becomes more complex, fatter, a higher dimensional chaos. But it's still constrained by an attractor. They hope there will be a series of attractors specific to different levels of mental activity. Rapp thinks the brain embraces chaos because this unique combination of order and randomness helps the problem-solving job it was designed to do.
One is compelled to ask the question, what functional advantages can chaotic behavior actually provide? One of the areas where it's fairly clear that advantages can arise is in the area of optimization. Sounds complicated, but it's not. Essentially the notion of search, the search for the best solution. What a certain amount of turbulence in that search can do is help you avoid becoming preoccupied with a small-scale solution and possibly lose sight of a much better solution. It's almost a forest and a trees phenomenon. What you want to be able to do in optimization is to scan a wide range of possible solutions and to avoid locking on to a suboptimal solution early in your search. One wants to have a certain amount of turbulence or randomness in that search. However, this randomness has to be a controllable randomness because eventually one wants to converge onto a solution. So you require something which seemingly is self-contradictory. You require randomness, because that's going to be quite helpful to you, but it has to be controllable in some way. And that's exactly what a chaotic system does, because it is extremely disordered, profoundly turbulent, but it is a deterministic system. It responds to controls in a deterministic way. And that means that, in fact, it will be subject to control by the central nervous system itself. It's a beautiful biological device.
By learning to distinguish between utter randomness and the constrained randomness of chaos, scientists like Paul Rapp are extending Newton's cause and effect determinism into the strange new world where order and randomness combine. Thanks to chaos, scientists are beginning to model the real world in all its non-linear complexity.